introduce Jerome Busemeyer, who is a faculty member in the Psychological and Brain Sciences Department. He did his bachelor's work at University of Cincinnati and then PhD at University of South Carolina, and now he's a provost professor, which is one of the most prestigious titles that IU gives to faculty in psychological sciences. So really happy that you agreed to give a talk today, and really looking forward to it.
Okay, thank you. I guess I'll try to stay in the middle here a bit. Okay. Well, hello everybody. So let me begin by saying I'm talking about quantum probability theory here, and we don't need quantum computers and we don't need quantum brains for this application. I mean, it'd be nice if we had quantum computers, but we don't require quantum computers. But what we're just doing is we're just using the mathematics of quantum theory. So that's, and I had to change the title slightly because Rich Schifrin was making fun of me, so the title's changed to Applying Quantum Probability Theory to Data from Big Data. You'll see why I made that small change later. Okay, so what I'm going to do is first I'm going to talk about, I don't think everybody knows about quantum theory, so I'm going to give you a 15-minute tutorial, teach you everything you need to know about quantum theory in 15 minutes without the partial differential equations. Yeah, and so what we're going to do, though, is we're going to compare quantum theory to classic probability theory, which is probably what everybody knows, so our Kolmogorov theory. And then I'm going to just briefly talk about research that provides evidence for quantum probability theory when applied to human judgment decision making. But not going to spend a lot of time on that, but a little bit just to show you why we got interested in this and why we think quantum theory might have some relevance to human decision making. And then we'll talk about applications to data from big data and some conclusions. So first of all, let's compare these two theories. So it's interesting that classic probability theory, they call it classic because it was around for a long time, with Laplace and Lagrange and all the French mathematicians who worked on probability theory in the 1800s, but it wasn't finally axiomatized until 1932 or 33 by Kolmogorov in his book, famous book, where he axiomatized it. About the same time, now quantum theory, of course, was developed in the 1920s and 30s by a number of famous physicists like, Bohr and Dirac and, Heisenberg and Schrodinger and these guys. And they didn't really know what they were dealing with exactly until Dirac and also von Neumann axiomatized quantum theory about the same time, 1932, 1933. And so we have these two axiomatic theories. Now, the nice thing about, classic probability theory has already been applied. It started from a lot of classic theory started from physics, but it's already been applied all over the place, economics, social sciences, even cognitive science. But quantum theory has only been applied to physics primarily. But once you axiomatize a theory, and you take the mathematical structure out of the context, you can see how you can apply it to other areas. So just like geometry, at first we thought there was one Euclidean geometry. We discovered there's other geometries. And now all these geometries, they arose in physical problems. They're used in all kinds of applications. So what we want to do is we want to take the axioms of quantum theory and see if they're applicable to problems outside of physics. In particular, we've looked at human judgment decision making, and we'll be looking at some big data, data from big data applications today. Okay, so let's try to briefly, in a short time, kind of give you the idea how this theory works. And in order to do this like in 10 or 15 minutes or even less, let's just keep it simple, so we'll work with finite spaces. Probability spaces can be continuous, uncountably infinite, or countable, or finite. Let's just use finite so I don't have to do too much work here. But let's suppose it could be a large finite space, 1 billion or 80 billion if you want, but finite. But so if we have a classic theory, we have something called a sample space. So the whole idea of Kolmogorov's theory is to place everything in set theory. It's based upon set theory. So sample space is the set. The universal set contains everything. An outcome that you can realize in some kind of experiment or situation it's a point in that sample space. So that's how we begin with Kolmogorov's theory. Now, quantum theory, what we do is we replace a sample space, which is a set, with a vector space. We call it the Hilbert space. So if you want, let's suppose you had 100-dimensional, let's say you had a sample space of cardinality 100, for example. Well, you could build then a corresponding Hilbert space of dimension 100. So that would be the idea. So we're just changing from sample space as a set to a vector space. Now, the outcome, a point in our sample space, would correspond to an array, one of those orthogonal arrays in our vector space. So if we had a 100-dimensional vector space, each one of those axes would be a single outcome. So an event in classical theory is a subset of the sample space. So that's the key. That's one of the key ideas, of classical theory. And that's what, once you do this, you're buying into a logic. And so you're buying into a Boolean logic, because the logic of sets, the algebra of sets are like one-to-one with the Boolean logic of propositions. So you're buying into this logic. You're buying into things like, well, if you have an event A, you have another event B, well, we have closure. We have an event A and B, which is the intersection. If we have an event A and B, we can have event A or B. And we have an A and B is commutative. A and B is the same as B and A, because it's intersection. A or B is the same as B or A. So it's commutative. It's a commutative logic. Also, it's distributive. So A and B or C is A and B or A and C. So we're buying into all these axioms at once. Now, in quantum theory, since we're working with this vector space instead of subsets, an event is a subspace. So a subspace might be a single ray. That would be one of those unique outcomes. Or a subspace might be a plane like this table. Or a subspace might be a three-dimensional subspace in a higher dimensional space. So we have subspaces for our events. So that's the key thing that von Neumann introduced here. And so once you introduce the idea of events being subspaces, you're buying into another logic. You're buying into a different kind of logic. Mike Dunn's here. He's did a lot of work on studying these kinds of quantum logics, or generalized logics. Yeah, so the logic of subspaces is not the same as the logic of subsets. So first of all, closure doesn't always hold. So if you have an event A and you have an event B, there's something called incompatible events. If A and B, and I'll talk about incompatibility a bit later, but they can be incompatible. So if you have an event A and B, there is no A and B event. If you have now you could have an event A and event B and what we call compatible, then there is an A and B. So sometimes you can have an A and B and sometimes you can't. So you don't have closure. Now if you have things that are incompatible, if you have an event A, you also have an event B, there's no A and B, but you have an A and then B. So you get a sequential notion. You can observe A and then B, or you can observe B and then A, but the order matters. So you lose commutativity with some of the events. And also, the distributive axiom doesn't always hold. So the distributive axiom will sometimes break down. Sometimes you have an event A, but A is not equal to B. Well, the event A, parentheses, B or not B, that's okay. But that's not necessarily equal to A and B or A and not B anymore. The distributive axiom will sometimes break down in quantum theory. That's like an interesting property of quantum theory. That violation of distributivity, well, let's back off a second. The distributivity that you get in the classic logic with the sets leads to the law of total probability in probability theory. But the breakdown of distributivity in quantum theory leads to what we call the interesting interference effects, which is the magic of quantum theory. So anyway, we're changing. So this, a lot of people think, what makes quantum theory quantum? It's the idea that you're defining events as subspaces instead of subsets. Now, another thing about classic versus quantum theory, let's say in classic theory, we have a state. I mean, you often probably don't use this kind of a word state to describe things, but state is your probability function. So you got this probability function, and it's used to assign probabilities to all the events. So if I'm judging probabilities for events, I have a state. If Jim Townsend's judging probabilities for events, I wouldn't trust his judgments, but he has a state, and it's quite different than mine. So we all have our states, you know. We all have our ways of assigning probabilities to events. So the state in a classic theory is this probability function. Now in quantum theory, it's a little bit different. So in quantum theory, so we have this vector space, and then we have this state vector which is a vector in your vector space. So you got this vector, and it's a unit length vector. So it's sitting out in this vector space. And so the way we compute the probability of an event in quantum theory is we have our subspace, that's our event, so like this plane, and we take our vector, we project that event onto the subspace to get the projection, and that squared projection then becomes a probability. So that's how we compute probabilities. How many people are familiar with this operation? Yes, a few people. How many people have done multiple regression before? Usually I get a lot of hands. Anyway, if you've done multiple regression, you also did this, because this is exactly what you do in multiple regression. The R squared is your squared length of your projection. So that's how, so far that's how quantum theory works. Now, a couple other pieces, then we can move on. But you know, we need to introduce the idea of a conditional probability. So in classic theory, if we know that event A has occurred, and now we want to provide a new probability function, knowing that event A occurred, we construct what we call a conditional probability function. So we take our original probability function, and we construct our new probability function by taking our original the joint probability of event B and A, and we normalize by the probability of A. That's the event that occurs. So the new probability function sums up to 1. That's the normalizations for it. In quantum theory, we do something similar. So this is looking at the probability event that B occurs after we've observed that A has occurred. So we take our state, that's this S, that's our vector. So like let's say if we had a 100-dimensional space, this vector S would be a 100 by 1 vector, and it's sitting in the vector space, unit length. And then piece of A, that would be the projector corresponding to the subspace for event A. And that's basically, it's a matrix, and it would be a 100 by 100 matrix. And P of B would be the projector corresponding to the subspace for event B. So we take our state S, which is a 100 by 1 vector, we multiply it by this projector P of A, representing the subspace for A, and then multiply it by our matrix P of B, representing our subspace for B. It's like a joint probability, but it's sequential. It's the probability of getting A and then B in the numerator. And then we normalize so that everything sums to 1. And so that's how the quantum works. But what we lose is the commutative property that we talked about before. So the probability in classic theory, the probability of B and A, of course, because the events we're talking about are sets, and A and B is defined as the intersection, so that's commutative. But in quantum theory, things are not always commutative. So sometimes they don't commute, because these matrices, anyway, like you might remember from matrix or linear algebra, every subspace corresponds to a projector. So this projector is an operator that takes your vector and projects it onto the subspace. So anyway, so these matrices correspond to our subspaces. But as you know from matrix algebra, the product of matrices doesn't always commute. So if the product, projector A times projector B is not necessarily the same as projector B times projector A. That's what we mean by non-commutative. Now sometimes they do commute. If they do commute, then you have the same result as classic probability theory. If they don't commute, you get something different. In fact, if everything commuted, so there was no non-commutative events, then quantum theory would be identical to classic probability theory. There wouldn't be any difference. It's only when you have this non-commutativity that this happens. Okay. Now, just to get this idea of commutativity. So, this is a really important issue in quantum theory, commutative versus non-commutative. So I have this example here. This is a 3-dimensional Hilbert space. Actually, it's a real space. I mean, Hilbert space can also have, we actually use a complex field, but that's not important for us right at this moment. But anyway, we have two panels here. And so focus yourself on the left panel, what I call the self perspective. So imagine, in this example, imagine like, imagine me as a teenager growing up in the 60s. Yeah, I'm kind of old, Jimmy Dean time, And we had these cars, we used to go out at night and maybe drink a little beer, and then we get these car games where we have two cars running towards each other, and somebody has to play chicken, somebody has to deviate out. If both cars run into each other, we just crash into each other. So basically, you have three options. You can go straight, or you can go to the left, or you can go to the right. But we both might choose to go to the left, or we both might choose to go to the right. Anyway, so I'm playing this game with an opponent, and so let's suppose I'm looking at what to do from my perspective. I call this a self perspective. So I'm thinking, what should I do? And I'm thinking about what I should do. And so let's say the A-axis is I go left, and the B-axis is I go right, and the C-axis is I go straight. So this is a three-dimensional. Those are three events. Those are three things I can do. And let's say this is my state vector. I'm sitting right here at S. So there's, in this unit length. So that's going to be used to compute my probabilities. Now, if I want to compute, well, what's the probability that I go left or right? That's this plane. Now, those two events, left and right, are commutative because they're in the same basis. So they're going to commute. Anyway, so we have an or here. What's the probability I get left or right? And since A and B events commute, we can compute the probability of the or, and the or is just going to be this plane. So I take my state vector, I project down to this plane. The projection is t. I get the squared length, and that's my probability that I go left or right. So that's the things from my perspective. But so here's why I think quantum theory is interesting to humans is it's hard to think about your own perspective and your opponent's perspective at the same time. I can think about myself, what I want to do, but if I want to think about like what Jim Townsend's going to do, he played this game more often than I did probably. But anyway, if I want to think about Jim, I had to put myself in his shoes, And so I had to change my perspective. And this changing perspective is like rotating the basis. So you're looking at the world from a different perspective. And so that new change in the basis is going to give you new probabilities because now I'm looking at the world from, Jim Townsend's reference point. And so in this right panel, we have this new basis, U, V, and W. This figure, it's kind of projected, so it doesn't look exactly right. But we basically orthogonal rotation. So we've rotated A to U, B gets rotated to V, and C gets rotated to W. And so I have the same state vector here, S. It's the same one I had before. So I got the same state vector, but now I'm using a different basis to evaluate events. So now, like, V is the event that Jim is going to go, let's say left. I'm losing track. But let's say V is the event that Jim's going to go left, which used to be my B. But that's Jim's event going left. I take my same state vector, and now I'm projecting on V that Jim will go left. The squared length of that projection's R, and that squared length gives me the probability for Jim. So I can compute the probabilities from my perspective, and I compute the probabilities from his perspective, and I do it all in the same three-dimensional space. Now, if everything was compatible, if everything was classical, like classic probability theory, we'd have to have a 9 by 9 space. Well, the probability sum up to 1 would be 9 times 9 is 81, 80-dimensional space for classic probability theory, because you have to have all the joint probabilities, right? You'd have to have the probability, I'll do this and he does that. I've got three things, wait a minute, is that right? No, a 9-dimensional space. 3 times 3 is 9. I'm not good at arithmetic, that's for sure. Anyway, it's a 9-dimensional space. So the quantum works in a 3-dimensional space because I keep the 3 dimensions I rotate around. But in classic probability theory, you keep expanding the space. Like if I had 3 players, 3 cars coming out each other, we have 3 by 3 by 3, it's 27, right? So it blows up. So the quantum model would just rotate around this three-dimensional space. I'd rotate one perspective for Jim, maybe another perspective for Rich. Rich would never play this game, though. But, you stay in the same three-dimensional space. But in classic probability, the space is blowing up on you because each time you have a new player, all these events keep getting crossed. You have to have all this closure, and you blow up the space. So maybe that's why Mother Nature built us this way, because we've got lots of questions to answer, and we can't just keep exponentially growing the size of our probability space. We have to keep bounded. So this lets you have a bounded space, but ask lots of different kinds of questions within a bounded space. Okay, that's the 15-minute introduction that we have here. Now, just briefly, what's some kind of evidence for this theory in human decision making? Well, I'm not going to go through all these papers, then I would never get to the big data problem. But we have examples of interference effects of categorization on decision making, interference effects of choice on confidence. These interference effects are kind of a signal. It's like if you ever heard of a two-slit experiment, you get the interfering waves in quantum theory and quantum physics. We get these effects also in psychological experiments. We have papers using quantum theory to explain question order effects and similarity judgments and probability judgment errors. So I'll briefly show you an example of this last one, probability judgment errors. Okay. So this is a brief example, but the original studies were done by Tversky and Kahneman, reported in 1983. Danny Kahneman won the Nobel Prize in economics. Tversky died. He couldn't get it because he's dead. They only give it to people that are alive. But anyway, they're really famous for this kind of work. This is just one of the works, but this is the kind of work that they did. We wrote a quantum paper to try to explain these results that was published in 2011. So anyway, I don't know if you're familiar with this, maybe some of you are, but basically you're told a story like this. This is just one example story, but you're told a story, like you're told this story about Linda. So Linda was a philosophy major and a student at UC Berkeley, and she was an activist in the social welfare movement. So that's some prior information. So in a Bayesian model or something, you get a prior from that. And then you're asked to rate the probability of some events, like, well, what's the probability that Linda's a feminist? Or that seems likely, possible. This study was done in 1983. This whole business of feminism was really more important, perhaps, than it is. Well, I don't want to say that. Anyway, that was a big thing. Anyway, it sounds like Linda could be a feminist. What's the probability Linda's a bank teller? It doesn't sound like she could be a bank teller. Anyway, so these are the kind of questions. Well, here we have a conjunction question. Is Linda a feminist and a bank teller? Or is Linda a feminist or a bank teller? And these are the results that you get. Now, this is one study, but we get these results. This has been replicated many times with different stories. I mean, you don't always get this kind of result, but a lot of stories can produce this result systematically. So here, Linda's a feminist. They rate it really high, 0.83 probability that she's a feminist. That's fine. Bank teller's rated low. It's only 0.26. That's fine. There's no problem there. The problem arises right here. We call this the conjunction fallacy, because people think it's more likely that Linda's a feminist and a bank teller than a bank teller. That doesn't make sense, right? That's a violation of the conjunction. And then we have a disjunction fallacy. The probability that she's a feminist or a bank teller is only 0.6, but the probability she's a feminist is 0.83. So that's a problem. So these are kind of unusual. These were Stanford students, by the way. Now, some of them didn't have statistics, but these were Stanford students. You can also get these results with medical doctors with medical problems. So, this is a violation of the law of total probability. So here's the probability that Linda's a bank teller. Well, that's going to be broken down into two parts by the distributive axiom, right? That follows from the distributive rule of logic. Probably she's feminist, probably she's bank teller and feminist, plus the probability she's not feminist and bank teller given she's not feminist. Well, these two terms have to be greater than this term because this is the same as this term, and this has got to be a positive number or 0, and this is the joint probability. So anyway, that's a violation of the total probability. So let's take a look at how the quantum model works. So here's the quantum model. So here, S is the state, in some perhaps a high-dimensional Hilbert space, 100-dimensional, 1,000-dimensional. We don't really need for the argument what the dimension is, but you hear this story, so you got this vector sitting in your Hilbert space representing the story. And then you have a projector representing bank tellers. So bank tellers, like all the features that describe a bank teller, all those features gives you some kind of subspace in this vector space. And so we take our state, we project onto our bank teller subspace, and we get the squared length. Now, this is Feynman's famous, most popular trick. We always stick an identity operator in the middle. Now, this identity operator doesn't do anything because identity times S is S. But then we unpack this identity operator into two parts. So P of F, that's the projector corresponding to the subspace for feminism. And then P of not F, that's the orthogonal complement. That's the projector onto the not feminist. And they both sum together to become the identity, because you're either one or the other. So that's the entire Hilbert space when you combine the two. So this becomes that. And then we multiply through here, we get to this point. Now this middle spot right here is the famous superposition state. So this is their superposition state, because in this state, you're in a state where you're unresolved regarding the feminism. You haven't made up your mind about feminism. You weren't asked about feminism, and so you're superposed on the feminism question. So that's why you're linearly combining the two in the superposition state. And that's what gives you the strange behavior in quantum theory, because when we get the squared length of the superposition, we're going to get the first term squared, which is right here, and then the second term squared, which is right here, but then we get the cross product terms. We get this term times this term and this term times that term. That's the interference term. That produces the interference effects in quantum theory. And so this is the interference displayed right here. Now this interference effect, it can be positive or negative or zero. And so now if feminism commutes with bank teller, then I can move this projector for feminism before bank teller, and then it multiplies times not feminist, and it goes to zero. And so if things commute, the interference goes to zero, you get classic probability theory. But if they don't commute, then this interference term can be positive or negative. And what we want to explain our results is we want this interference term to be pretty much negative, so that it cancels out this positive part and lowers it below, so that this probability plus this overall negative because of the interference, this will be overall negative because of the interference. This will turn out to be lower than just this by itself, because this part here becomes negative. So that's how the quantum theory would explain that result. Of course, it's post hoc right there. Of course, you have to make a lot of other predictions to make the theory interesting. So we have about a dozen other predictions from the same model. Like this same model exactly also explains the disjunction fallacy. I'm not going to go through all the derivations here, but and then it also explains a number of other findings. And so we can post hoc explain the conjunction fallacy, but then we can a priori make a lot of other predictions that I won't be going over today. Okay, so let's turn to applications to big data. Now, one thing that really is an application to big data, but I don't do this, I have colleagues that do this, are people in information retrieval. So I have a colleague, Peter Bruse. Peter and I have a book together. Peter's actually in computer science. He does information retrieval. So he actually does work with big databases, like medical bases, things like that. Anyway, they're using quantum theory. They're basing their work on a book by Keith van Rijsbergen. It's called Geometry of Information Theory. So what they do is they treat a document as a vector in the Hilbert space. And then they treat a query as a subspace. So we use a projector. So we have a document that's some kind of vector that you numerically scale and normalize. And then a query would be a matrix, a projector. Now, sometimes these projectors will commute, and sometimes they won't commute, and so then you'll get, you can get sequential effects. And the reason why the quantum theory is kind of nice for information retrieval is you get, the sequence that people are asking questions is often very important for the answer that they're looking for. And so this is path-dependent. This is a path-dependent search process that you get from a quantum search. But I'm not doing that. That's what Peter Bruse and some other colleagues are doing. So what I'm doing, I might call data fusion and integration. So this is work with my colleague Joyce Wong. And so we're trying to develop what we call a Hilbert space multidimensional model for multiple contingency tables. So here's the idea. So this is why I'm calling it quantitative theory applied to data from big data. Because when you do a query from big data, of course, you're extracting information and you're summarizing the information, and you're summarizing it often in terms of contingency tables. You might summarize it other ways, but often, like in medical work or consumer choice work and other areas, they're getting probabilities of combinations of events, of features. So the idea is that you have these queries from big data sets, and they're being summarized by collections of contingency tables. So you might have one query might lead to a 2x3 table involving A and B. Another query might lead to a 5x5 table involving B and C. Another query might lead to a 3x3x3 table involving A, B, and C. So you get a collection of tables from different queries. And then you would like to have some kind of low-dimensional coherent representation of all these tables that you're getting. So that's our objective. So we want to build a low-dimensional representation to reproduce these tables and provides a simpler and more coherent understanding of the results. So let's just give an example to spur your imagination. So, suppose you're looking at queries made from a large social media source about political candidates. You could ask about how attractive somebody is, how honest they are, how intelligent they are, or how unusual they are, or unusual, let's say. And then you get frequencies of responses. Now let's suppose, in my example, we're going to get frequencies of responses to pairs. Like, how often did they say he's attractive and honest? How often did they say he's attractive and intelligent, for example? Now you could also get, how often did they say attractive, honest, and intelligent? I'm just not going to cover that example, but that's perfectly within the realm that we're talking about. Of course, if you ask too many conjunctions, you get smaller and smaller frequencies, and so you can't have too many conjunctions. Also, as we'll see, when you ask these questions, they're order dependent. So if you have like 3 conjunctions, you really need to look at all the orders, 6 orders, because it depends on the order. Okay, so another example might be, you have a large medical source, and you're asking for patient symptoms like, I'm using these letters because from now on we're using these letters instead of these examples. But like you might ask about anxiety or hyperactivity or, what did I put there? Irritation or unruliness, and get these frequencies for those pairs. Or you might have a large consumer choice source that you're working with, asking about food products, about how appetizing or healthy. Anyway, these are just to give you some examples. And humans are, of course, making these judgments, and you're collecting the data from some big sources on these human judgments. And so what you might end up with something like this. So now, each row here is a 2x2 table. Now, they don't have to be 2x2 for the theory that we're working on. I use 2x2s as an example. But there's 8 2x2 tables. So this first row is a 2x2 table. I've just taken the 4 cells in the 2x2 and just stretched them out to the 4 columns. So here's a cell where you said yes to both. Like, let's say this is the political candidate. Is he attractive and honest? So we're asking, attractive and honest. Here's the probability that we retrieve that they're yes to both questions. Here's the probability, yes, he's attractive and yes, honest. Here's yes, he's attractive and no to honesty, 0.101. No, he's attractive and yes, he's honest. And no, he's not attractive and no, he's not honest, for example. Now, this is a hypothetical data set. Now, we have real data sets, too. But I don't want to use the real data set because this hypothetical one is designed to show you all these problems that you could run into. So this data set contains all the problems, has all the problems. Our data set has some, but not all the problems. Anyway, here we're asking, is he attractive and intelligent? Here we're asking, is he honest and intelligent? Now here we're asking, let's see. Here we're asking, is he honest and attractive? So we reverse the question right here. So anyway, we can get different orders and things like that. Okay, so that's like an example that you might retrieve from a large source, and you might get these kinds of tables. Now, maybe what you'd like to do, and in fact, what they often do, is you want to build a Bayes net for this. Really nicely, succinctly, coherently explain all these kind of relationships. This is an example of a Bayes net, right? So, here we have honest. It influences attractiveness, and then attractiveness, honest influences attractiveness and unusual. I guess honesty and political candidates would be unusual. And attractiveness influences unusual and how interesting and so on. So we got this Bayes net. And anyway, so this Bayes net is kind of nice because it doesn't have that many parameters because we need one parameter. These are binary, so we need one parameter for the probability that he's honest. We need two parameters for the probability of attractive given honest because he can be honest yes or honest no. And then we have 4 parameters for probability of uncertain given attractive and honest. So we'd have like so we have 3, 7, 11 parameters in this Bayes model to explain all those tables. So that would be cool. Explain all these like, we've got 8 tables and they got 4 rows, 32 data points, And with these 11 parameters, we can reproduce we can make a joint probability. So down at the bottom here, I got the joint probability that the person's honest, yes, attractive, no, uncertain, no, and intelligent, yes. And so, with this Bayes net, we can compute all the joint probabilities, even if we don't see them. If the Bayes net works, we can compute this. From these joint probabilities, we can compute any of the marginal probabilities in the tables. So then we got this. This is not quantum, by the way. This is traditional. Right? So we'll get to the quantum. But yeah, so in this classic probability model, here's the hypothetical joint probability distribution. We got these 4 binary variables, A, H, I, and U. And these are the 16 possible combinations. We don't get to see this, but we might be able to infer that it exists. So this model, this would be a general model. The Bayes model is a special case of this. This general model has 16 parameters in it. Of course, they sum to 1, so there's 15 degrees of freedom. So the question is, does this exist? Can this general model reproduce those tables? Turns out the answer is no. Cannot. Well, anyway, how this works, for example, if we want to reproduce the table, let's say we take the table attractive and interesting, then we're going to pull all these red cells where the answer yes to attractive and yes to interesting are going to be these four red rows, because here A is yes and I is yes, A is yes, and I is. Those are the 4 rows. So those 4 rows from this latent joint distribution would be used to compute this observed probability of yes to this table. So that's how this model would work. But we can compare this to what we call a saturated model. The saturated model, instead of saying there's 4 latent variables, says there's 16. In other words, each table is a separate, completely separate conditionalized distribution. They don't have any common joint distribution. So that's what we call a saturated model. So this is the perfect model. This perfectly reproduces the data. So we can ask, is there any deviation between our 4-dimensional joint distribution and the saturated model? So we can do a statistical test. And it turns out that, I'm going to skip over some details of doing a statistical test, but we have log likelihood ratio methods for statistically testing that 4-way joint distribution. And you can show that this model fails for that data. But why does it fail? Okay, why does it fail? Well, this joint distribution has constraints, a lot of constraints actually. One of the constraints is that the marginal probabilities have to be the same. So this is a table of marginals. So here we're looking at the marginal for A when it's paired with I and U, because the joint distribution is going to compute the same marginal in both of those tables, right? And so this marginal here has got to be the same as this. And now in this table it is. The marginals are holding, and in these 4 rows the marginal holds. So that's not a problem in these 4 rows. So the marginal is satisfied there. But the trouble is it's violated in other rows. So first of all, like in this table here, the marginal for I, that's when I is coming first, which is right here, is different than the marginal for I when it came second. That's over here. So we're getting some differences in the marginals. Now in this case, the difference in the marginals is coming from order effects. So we have violations of marginal. We also have violations of order because the 4-way joint probability model doesn't allow any order effects because you have an intersection that's commutative. So you can't have any order effects with the joint probability model. We also have another kind of interesting violation. This comes from quantum physics actually, but this is not a physics experiment. But these 4 rows right here, I'm going to have to go through this quickly, but these 4 rows correspond to what we call the Bell test. You know, the 2 particles collide, they go over here, and we do a test over here, we do a test over here, and somehow, you know, we get this correlated pairs in these tests, and they violate classic probability theory. Well, anyway, there's something called the Clauser-Horn-Shimony-Holtz inequality that you can compute from all these joint probabilities in these 4 rows right here. They're measuring something about the correlation. The joint probability model, the 4-way joint probability model, only allows certain kinds of correlations. It's constrained in the nature of the correlations. Quantum theory can allow stronger correlations than permitted by classic theory. In this Clauser-Horn index, the classic probability theory, this index has to be 2 or less to be a classic probability theory. It's over 2, it's 2.25, so that's a violation. So we violated it, even though these 4 rows satisfy marginal, they also satisfy, there's no order effects, but the correlations are too strong. So we violate the CHSH. So those are 3 ways you can violate the joint distribution. Actually, the quantum model has a bound here too. The quantum model has to be less than 2 times the square root of 2, which is like 2.8 or something like that. Well, this one is below the bound right here. So how we do it better with the quantum model? I only got 15 minutes left to do this. So what we're going to do with the quantum model is we're going to take all these 2-way tables or whatever tables we have, and we have to first determine which variables, like we have A, H, I, and U, which variables are compatible and which variables are incompatible. Compatible means there's going to be no order effects, and the marginals will be satisfied when they're compatible. But we'll get order effects, and we'll get violations of marginals when they're incompatible. And then we have to determine the dimension of the Hilbert space. Now, we don't know the dimension of the Hilbert space, so we do something like multidimensional scaling. We start with the smallest and work our way up 1 step at a time. So that's what we're going to do. And then we can do a fit and see how many dimensions we need to fit the data. We want to fit it as small dimension as possible. So then once we find the dimension of the Hilbert space, we're going to determine our vector in our Hilbert space. That's going to be some parameters. That's like our prior, like in the Bayesian model, your prior. And then we have to, for each question, we have A, H, I, and U. We got 4 questions, or binary. We have to, or 4 queries. We have to build what we call a measurement operator. We have 4 measurement operators we have to build. And I'll show you how we build those briefly. And then we can estimate the parameters of these initial states in these measurement operators and do a log likelihood ratio test on the quantum model. We can actually compare the quantum model log likelihood ratio test to the Bayesian model, or for the joint distribution model. Okay. So like now I have to go quickly because we only got 15 minutes, but so basically when we look through our table of those 8 questions, what we would find that these questions, A and I, A and U, H and I, H and U, these are all compatible. The order doesn't matter and the marginals are satisfied in these cases. But these down here, A and H, are incompatible. The order matters and the marginals are being violated. So we're going to set these to be compatible, these to be incompatible. Now, if we're looking at the minimum dimension, if we have 2 compatible, we have at least 2 compatible binary variables. So the smallest dimension that the Hilbert space can be with 2 compatible binary variables is 4. Because we have to have all, like if they're 2 compatible, we need to have a yes on one of the compatibles, like a yes for one of the compatibles, a yes on the other compatible. We have to have those 4 combinations. But the incompatible, we're going to rotate. So we got 2 compatible pairs that require 4 dimensions at least. They could be higher, but we could try 4 and see if it works. And then the incompatible, we're going to stay in that 4 dimension and rotate around. So then we have initial state. So if you have a 4-dimensional space, we have these 4 initial parameters. These are called amplitudes in a quantum model. And so the length of this vector has to be 1. Now in quantum theory, these coefficients right here that represent, those are the coefficients that locate your state vector in a vector space. They can be complex numbers, but we usually start out with real. In fact, they often do that in quantum theory too. But they don't have to be real, but we start out with real. So we'd have 3 parameters here. And we usually start out with what we call an entangled state. So one of these entries is not the product of 2 answers. Like here's a yes to the one question, here's a no to the other question. this amplitude, there's some dependencies, like a conditional dependency, like in a classic theory, there are dependent events. Then we build our measurements. Like in this case, our measurement operators are going to be 2 by 2 matrix. So we start out with a Hermitian matrix. This is what we call a Hermitian matrix. Its conjugate transpose is equal to the original matrix. It's like a symmetric matrix. Actually, our Hermitian matrix is going to be real. We don't need to be complex. So these will be real numbers. And so it just has to be a symmetric matrix. So we got 3 parameters, H1, H2, and H3. And then we take this matrix exponential right here. This is doing the rotation. This is a rotator in quantum theory. I mean, in any theory. This is the unitary rotator. And so this unitary rotation then it provides the basis vectors for our yes and no answers. And so then we form our projector for a yes and a no answer from these basis vectors that we get from this unitary matrix. And so we do this for each question. So we build this for the attractiveness, we build this for the honesty, we build this for the interesting, and we build this for the unusual. So now we've got one state vector, it's 4-dimensional space, and we got these 4 measurement operators. And then we can use the quantum algorithm that I showed you before. It looks a little bit more complicated here, but it's the same algorithm. It's got a little bit of extra matrix algebra in it, but anyway, it's just computing the sequential probability right here. So right here we're calculating the probability to say yes to attractiveness and then saying no to interest. Now, in this case, they're compatible, so this order doesn't matter. Down here, this is probability to say yes to attractiveness and no to honesty. In this case, they're incompatible. The order does matter. So we can get the order effects from this model and also the violations of marginal from this model. And so then we go ahead and we have like 3 parameters in our state vector, and we're going to have 12 parameters in our observables, our measurement operators. So we have 15 parameters. And so now we can do the same thing we did with the joint probability model and test to see if it works with the data. So I actually took the table of data and I fit this model to that table, and it fits perfectly. Why does it fit perfectly? Because I generated the data, of course, from that model. But I generated the data from the model, and then I actually went back and see if I could fit it, and it does recover the model. What this is showing, though, is that you can get a table that's extremely complicated looking from a classical point of view, and you can build a very simple and elegant quantum model to reproduce all those tables in a nice, neat way. So it's more of a existence proof that this thing works. Now, in this example that I just showed you with these 2 by 2 tables, the 4-dimensional Bayesian model, the 4-dimensional joint distribution model had 15 parameters. And the 4-variable, 16-dimensional, 4-variable joint probability model had 16 parameters. They sum up to 1 to 15. The quantum model actually had 15 too. So we didn't really save any parameters in the 2 models in that simple case, except that the joint probability could not explain the results. We have violations all over the place, whereas the quantum model can't. But if you get into larger tables and more tables, am I going backwards? Oh, I'm going backwards. Sorry, me. So, sorry, I have to go through this stuff again. Yeah, larger designs. Suppose we have a little bit larger design, because 2 by 2 tables is kind of simple. We often have bigger tables than that. Let's just suppose we have these 4 attributes again, but we have 5 answers. Like you have a rating, like you like it, you dislike it a lot, you dislike it a little, you're neutral, you like it a little, you like it a lot, something like that. Anyway, you can have more than 2 answers to these queries. So if we have 4 attributes and 5 answers, and we also ask everything in all orders, because the order could matter when we ask. So we're looking at pairs again. Of course, you can even have more data points if you ask pairs and triples. But at some point, you can't ask too many questions. It gets too complicated. Anyway, there's going to be 300 data points in this data set. Now, in the joint distribution model, without doing some conditionalization like you would do in a Bayes net, Bayes net, of course, could reduce this number of parameters. But in a completely free joint distribution model, now you're going to have 625 parameters. So it blows up. So the point is, the joint distribution model blows up exponentially with the sizes. This quantum model is only going to have 69 parameters. So the quantum model is growing a little bit more linearly with number of parameters with the size of the data sets. So it's giving you a much more compressed representation than the joint probability model. Now, if the joint probability model works, and then you build a Bayes net model, you could get the parameters reduced down. So, but it doesn't always work. In fact, often it doesn't work, because very often you get order effects that violate the margins and violate the order, well, and then you might also get this correlation violation. So I'll conclude here that yeah. So we see incompatibility arising in whenever you're doing, big data queries where the source is coming from human beings, people buying products or reporting symptoms or, judging political people on certain attributes. You're going to get these violations like order effects, or violations of marginal invariance, and violations of these correlation effects. So you're going to have to deal with this issue. Some of these variables are going to be compatible, and some of these variables are going to be incompatible. And the number of parameters in our joint distribution model quickly exceeds the number of data points. And in many cases, no joint distribution model even exists. But the number of parameters in our quantum model grow much more slowly, about linearly. I mean, it kind of depends on the nature of the model that you're building. But it gives you a more efficient and coherent representation of these really, perhaps very complicated data sets that we're retrieving from these queries. So if I got you interested, maybe then you can take a look more. Now, this book doesn't have big data in it, but it is a book about quantum cognition. So thank you very much. I'll stop here. Yeah. So, questions? Yeah. Yes, Rich.
How often do you find data sets that the quantum model won't fit?
The quantum model won't fit? They don't exist, Rich. No, I mean, we've had pretty good success so far. So I received I got a paper to review from Psych Review where the title is, joint conjunction fallacy results that violate the quantum model. So there must be a paper out there. I haven't reviewed it yet. So it's possible to. The quantum model has a lot of strong tests, as Rich knows, and so it is easy to falsify this model. Well, just to give you an example, there's something called a QQ equality. When you look at 2x2 tables and you get the questions in different orders, so you get a 2x2 table in one order, a 2x2 table in another order, we have an a priori parameter-free, dimension-free prediction that we can derive, an exact equality that we derive from those order tests. And so far, when we've looked at large survey data from national surveys where they have large order effects, that QQ equality is satisfied. So we have strong tests, as Rich knows, and we've satisfied a lot of these strong tests, so we're encouraged. So you can get violations of this model, though. So it is easy to test it and roll the model out. Of course, every model is false, so it is a false model, but it's more successful than we think than the classical model for many findings.
Well, the question really, you have these data from humans that require, they have to explain away because they don't suppress the possibility that you have a quantum model which can explain a number of those puzzling findings in a less clunky way than, say, heuristic explanations they use for the Linda problem and so on. Now, if you get a violation of a quantum model in a different data set, then where do you go from there? Is that the U theory? What would explain?
Well, so this QQ equality was kind of tricky because if we got a violation, at the time I didn't see any way to fix the model. But more recently, though, quantum physics itself is not static. So the measurement theory that we're using that I presented to you from quantum physics here is the measurement theory from 1950s. Now the measurement theory in 2000 is much more complicated than quantum theory. So they have something called quantum noise models, and so you have much more complicated measurement operators. So we'd have to, if our simple measurement, we're using projectors. So we just take a projector that projects you onto the subspace. So, you know, our measurement is a subspace. But you can have more complicated measurement operators in quantum physics now. And we might need to turn to those. So we always have, there's a way out maybe. You know, we could use more complicated measurement operators. Like they're called partially observable, let's see, POMVs, POVMs, partially observable, no, what is it? Anyway, positive operator valued measurements. That's what they call them. They're a little more complicated measurement operators. So there's more complicated things we could turn to, yeah. Andrew.
Quantum neural nets?
There are things called quantum Bayes nets. I don't know about quantum neural, I mean, there are some quantum neural nets, but I don't think they've ever been very popular. I mean, they're not really, they're basically, quantum neural nets are basically just using complex amplitudes in a traditional neural net. They're not using quantum.
Information is amplitude, so there's a
Yeah.
new opportunity for interference effect.
Yeah, right, yeah, 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 yeah. Yeah, so there's quantum, you can have a quantum neural net, and you can also have a quantum Bayes net. Now, there's a lot of work with quantum Bayes nets. So quantum Bayes net would look just like the classical Bayes net, except you put amplitudes in there instead of probabilities in there. But then you'd also can allow rotation of those amplitudes in a quantum Bayes net, which you couldn't do with a classic Bayes net. But yeah, quantum Bayes nets are kind of discussed a lot in the physics literature, but we haven't used them. But well, one of my colleagues has actually used it for causal reasoning, looking at causal reasoning and using a quantum Bayes net to model the effects, because you get a lot of order effects in causal reasoning as well. And so they're using a quantum Bayes net to account for those. Yeah, Mike?
Yeah,
You know.
would it be a fair description of what you're doing? Is you're using quantum probability models to model irrationality?
That's kind of a tricky question here.
Yeah, I thought it was.
Well, so like the conjunction fallacy looks like irrational behavior.
It sure does, yeah.
However,
And there's nothing wong with doing that. You are a psychologist.
yeah, I know. No, but you know, so the thing is this. Let's change let's get the same results, but let's change it to Mother Nature Mother Nature's expressing her probabilities for spin. Okay, so if I prepare a particle in the up, and I ask Mother Nature, what's the probability that it's down? 0. Now, if I prepare the particle in up, and I ask, what's the probability that it's a plus state and down? Is 0.25. So Mother Nature does this too. In other words, Mother Nature will give the probability 0 to down, but the probability 0.25 to plus and down. So I mean, plus is like testing a different direction. So Mother Nature gives you these joint Mother Nature violates the conjunction rule as well. Now the reason why is because, and this is where you get into Bohr made this argument so many years ago. It's not really Mother Nature is not irrational, of course. She's brilliant, you know. So people are not necessarily irrational either. Now in the physics experiment, the reason why Mother Nature is not irrational is because you have to conditionalize on the entire context of the experiment. So when you're only asking the question down, you're asking what's the probability down when I only ask down. But then when you're asking plus and down, you're asking what's the probability of down when I ask plus and then down. You're conditioning on a different context. So you have to take the whole context of the experiment. So the human being, now this is a little bit trickier, but the human being would be like, well, what's the probability that Linda's a bank teller when you only ask me if she's a bank teller? Conditioned on you only ask me that she's a bank teller. And now what's the probability that she's a feminist bank teller given that you asked me that she's a feminist bank teller? So the bank teller in the conjunction question is not the same bank teller when you ask the loan. That's the thing. So it's not necessarily irrational if they're doing that. If the judge is actually behaving that way. Well, let me give you another example. People don't always like this one, but if I tell my dog, if I command my dog, sit down. I didn't train my dog very well. I got 3 German Shepherds, 2 of them are wild, and one's hyperactive. But anyway, if I tell my dog, sit down, I get a low probability he'll sit. If I say, get your ball and sit down, there's a high probability he'll do both of those things. Now, I predict he will do that. I predict get ball and sit down's higher probability than get down. There's nothing irrational about that. But I am saying a joint probability is higher than a marginal, conditioned on those questions I'm asking. So that's why this rationality issue is a little bit tricky, depending upon how you set up your state space. So if you put Linda in the same sample space with, no, I'm sorry, if you put bank teller in the same sample space with feminist bank teller, yeah, then you have to have bank teller be greater than feminist bank teller. But if you have bank teller in one sample space, but bank teller in the context of feminism in a different sample space, then it's not irrational.
Well, that's a very interesting example. Of course, in logic we have, besides strict logic, there's pragmatic sense of words. So like, why are you asking?
Yeah, right.
That's
Right.
very,
Yeah, right.
very interesting.
Yeah, right. Now, the dog thinks that too. Like, if you're asking me about the ball, of course I'm going to sit down. Yes, Jim.
Are there any ways in which homomorphy and probability theory is more general? You emphasized how the quantum can be more general by allowing non-commutativity, but are there any ways, possible experiments where you could actually decide in terms of a prediction from homomorphy and probability that wouldn't be predicted from a quantum theory?
Well, this is another kind of complicated question, but it's a good question. I mean, I'm not making fun of you, Jim.
Thank you.
But yeah, there's some kind of, there's a lot of discussion. Is quantum probability theory really a generalization of classic probability theory or not? And in a way, it's a generalization because quantum theory allows you to have compatible events and incompatible events, where in a sense, classic theory only has compatible events. And so in that sense, it's a generalization. However, it depends on how you want to define your Kolmogorov theory. So this is a little bit. So Kolmogorov himself, if you look at his book, never expected one sample space for the entire universe. So you can have separate sample spaces, and you can have a Kolmogorov theory where you have separate sample spaces. They're just unrelated. So this experiment's got a sample space. This experiment's got a sample space. So you can think of in quantum theory, when you're I use my arms a lot for these kind of things, but when you're in one basis, you pick one basis and you stay in that basis and you ask all your questions in that basis. Everything's compatible. That's like generating one sample space. But then if you rotate, now you got a new basis, and now you got new questions in this new basis. That's a second sample space. If you stay in that new basis, that's a complete Kolmogorov space as well. So this basis, whenever you stay in there, you got a Kolmogorov space. This basis, whenever you stay in there, you got a Kolmogorov space, but they're just two unrelated ones. In a Kolmogorov theory, you could say, well, you got one experiment here with this basis, one experiment here with this basis. This is Kolmogorov, this is Kolmogorov. So a generalized Kolmogorov would allow you to have a whole collection of sample spaces. Now, but then the beauty of quantum theory is that if you have a sample space here and you have a sample space here, quantum theory will tell you how the probabilities here relate to the probabilities here. So you can transform from one to the other. It gives you a way of moving from one distribution to another distribution, whereas separate sample spaces, you don't have any way. And so in that sense, the Kolmogorov is even more general because it doesn't tell you what the transformation is going to be. The quantum theory has an exact transformation that you got to use. Yeah.
Another way to answer is whether quantum model applied to a set of data is always more complex than a traditional model applied to the same data.
Yeah. Yeah, well, of course, Rich knows the answer to this. We compare to traditional. Anyway, it depends on the models you're comparing, but it's not necessarily, because many people say, well, quantum theory uses complex numbers, so it's got to be more complex, because it's got complex numbers. But we did a model comparison once with a traditional judgment decision-making theory, prospect theory from Tversky and Kahneman, and a quantum model. And if the quantum model was more complicated, the Bayes factor would reflect that and penalize it. But our Bayes factor strongly supported the quantum model over the prospect theory model. So at least that's an example where it's not necessarily the case that the quantum model is more complicated. But it depends on the models, I suppose. In this example I'm showing you here, the joint probability model is much more complicated because the parameters that grow exponentially. Of course, if you have a constrained Bayesian one, you can constrain it, but it might not work.
All right, so I think we're
Okay.
Thank you so much again.